Okay, welcome back everybody. I'm going to continue with 2D dynamics. Last time I went through two videos talking about just horizontal displacement given a horizontal velocity. And now I'm going to adjust this a little bit. So we're still going to deal with horizontal displacement given rather than horizontal velocity. I'm going to give you a resultant velocity and a launch angle. And we're going to ask the question, how far does a ball go when you pick it at a certain velocity and at a certain launch angle? And so in this case, I'm going to figure out whether or not kicking a ball at 5 meters per second with 40 degrees of a launch angle will clear 5 meters. So let's say you're trying to kick this ball over some kind of gap here, and we want to know, is this fast enough velocity, and for this launch angle, is this fast enough velocity to clear those 5 meters? I'm going to tell you how I would have solved this in undergraduate. As an undergraduate student in a biomechanics class, and then I'm going to go through some MATLAB code to show you how I solve things like this now. Okay, so what I would have done is I would have taken our resultant velocity vector, which is 5 meters per second, and I would have broken it down into its horizontal, which I'm calling x here, velocity in x, and its vertical, which I'm calling y, velocities, right? So I would have broken it down this way. I would just use basic trigonometry to do this. So for the vertical, I would have said sine 40 is equal to velocity y over 5, and I'll get 3.21, and then I would do the same thing, except instead of using sine, I would use cosine, right? It's adjacent over hypotenuse, sine is opposite over hypotenuse, and so I would have broken it down this way, and when you do this, you see that the vertical velocity is 3.21 meters per second, and the horizontal component of this velocity is 3.83. So the next thing I would do to see horizontal displacement is I would find the amount of time that the ball spends in the air. Because once I know time, it's really simple. I can just multiply time by our horizontal velocity to get horizontal displacement. So I would solve for t using our vertical velocity. Right? And to do this, it's relatively simple, right? We know that the change in velocity is going to be equal to the final velocity minus the initial velocity. Well, we just calculated the initial velocity. It's 3.21. We know that when it hits the ground, if it's hitting the ground at the same height, if there's no change in altitude, it's going to be the same velocity but opposite sign. And so we know that the final velocity is going to be the opposite, or the negative, of our initial velocity. So it's negative 3.21. We just plug those two things into this equation here. So it's negative 3.21 minus 3.21, and that's equal to negative 6.42. Once we know that change in velocity, it's really simple to get delta t. We just say delta v is equal to the acceleration in y, which is negative 9.81, or gravity, times delta t. We solve for t, and we see that the ball ends up in the air for 0.65 seconds. So then again, you just take that 0.65 seconds, you multiply it by our horizontal velocity. We're assuming that there's no wind resistance or assistance, so we're assuming that this velocity stays constant. We multiply by this time, and we see that the ball travels ultimately 2.49 meters, so just under 2.5 meters. What that means, unfortunately, is that the ball does not clear the 5-meter gap, and I guess we lose this ball. All right, so that's how I would have solved this problem as a student. If this came up on an exam, I would have walked through these steps, and I would have hopefully gotten this question right. Now I'm going to show you how to do this in MATLAB. Let's hop out of here, jump into MATLAB. Now I'm starting with the 2D kinematics code that I ended with. Let me clear some of this stuff out here. I am starting with the code that I wrote in part 1 of my 2D kinematics series, I guess you could call it. So if you haven't seen that, please go back and watch that video before you go through this one, because you're going to need to see how I got all of this code. I don't want to go through it again. Okay, so what we're doing is we're calculating horizontal distance for a given velocity and a launch angle. In the previous example, we needed to clear 10 meters. There was 10 meters at the bottom of a cliff of rocks that someone had to clear. Now we're trying to clear 5 meters, and we also need to add into this a launch angle, which for this particular problem is 40 degrees. This is in degrees. Oops. And this distance to clear is in meters. Always good to specify your units. Okay, our position y, position x are 0. Our velocities are 0, but we aren't given x and y. We actually need to solve for those first. Remember, that's the first thing I did when I solved the problem by hand. So what we are given is velocity r, or resultant velocity, and we're given that that is meters per second. All right. Okay, so what else? Do we need to change anything else? Acceleration is negative 9.81 in the vertical direction. That's gravity. That's not changing. Acceleration in the x, or the horizontal direction, is still 0. That's great. We're still assuming that wind resistance or assistance is negligible. Time is initially 0. That's good. Now I'm going to do two other things here. I'm first going to add an iteration variable because we're going to need to do something on the first iteration, but on no other iterations. So we need to track how many times through this loop we are going, and we need to know when is the first instance in the loop. And so I'm going to initialize j. I'm just calling this iteration variable j arbitrarily, and I'm going to initialize it as 0. And then the other thing I'm going to do is I'm going to add a sampling rate. And I'm going to show you why we do this at the end, because we're actually going to change this sampling rate and see what that does to our outcome variable, which is horizontal displacement. So our sampling rate, I'm just going to say is 0.01. This is how we're going to update time, which we're going to use for all of these equations, our time step, on each iteration. So right now it's 0.01, and I will add that sampling frequency every time in this loop to our time variable, which starts as 0. And we end up using this time step in all of our calculations for velocity and position. So what I'm going to do before I forget is I'm going to take our sampling rate, and I'm going to replace these instances where we call that time step in the code so that I don't forget to do this. And at the end of the video, I'm going to change that a bit, and we're going to see what that does to our output variable, our horizontal displacement variable. Okay, I think I got all of them there. Yeah. Okay, so far so good. So the first thing I'm going to do, we're going to hop into this while loop, and we're going to say while our vertical position is greater than or equal to 0. So while the ball is still in the air, it's greater than 0. You know, we can't have it go negative. That's going below the ground level. So while it's greater than or equal to 0, we're going to run these calculations. And this is going to give us a continuous variable for velocity, position, and acceleration. The first thing I'm going to do is go ahead and update our iteration variable. So I'm going to say j is equal to j plus 1. And on the first time through this loop, j is equal to 0 because that's what we initialize it as here. So the first time through is j is equal to 0 plus 1. So then it gets updated to 1. And then on the second time through the loop, it's j is equal to 1 plus 1, so then it's 2. On the third time, it's 2 plus 1, so it's 3, and then 3 plus 1. And it's going to do that every time it runs through the loop. Okay, so just in case you're not familiar with MATLAB's loop structure, that's what it's going to be doing. Okay, so you'll have to remember we have to take into account a launch angle here. After we take into account the launch angle, the ball leaves the ground and it's subjected to gravity and our horizontal acceleration, which is 0 because we're assuming wind resistance and assistance are negligible. So the code that I wrote in the first video is going to hold up here, but we do have to take into account that launch angle now. So we have to run those sine and cosine calculations that I did just a second ago inside of this code. But we really only have to do that once. So this is why I add this iteration variable. So I'm going to say if j is equal to 1, so if this is the first iteration through this loop, we're going to go ahead and take into account that launch angle. And if it's not, if it's anything other than 1, we're just going to keep all of this stuff the same. So I'm going to go ahead and indent this, make sure that it stays in line. In MATLAB, these don't have to be indented, but it looks a lot better if they are. It's easier to keep track of. Okay, so you have to remember we initialized velocity vertical and velocity horizontal, or y and x, as 0 up here. On the first time through, what I want to do is replace those zeros with what these velocities would be, taking into account the launch angle and our resultant velocity. And then on subsequent iterations, it's just going to run through the same code that we had before. And so what that is going to look like is, I don't know why this is telling me I can't, oh, that's why, is this. Okay, so we're going to say velocity y end. And so instead of calling end plus 1 and appending to this 0, we're just going to overwrite the 0 on the first iteration, and then in subsequent iterations, we're going to append. So velocity y end is equal to the sine of our launch angle, which was initialized up here as 40, and we are going to multiply that by our velocity resultant, which is 5 meters per second, which was specified right here. Okay, so I'm going to point out here it's important to use sin d or sin d instead of just sin, because sin d takes this launch angle as degrees. Okay, so it's important to do that. Otherwise, you're going to end up with different values. Okay, so now we're going to do the same thing in the horizontal direction. Now instead of velocity y, it's velocity x, and instead of using sine d, we're going to use cosine d. Same launch angle, same velocity resultant. Okay, so this should run. The last thing that I have down here is the same plot that we had before. It's going to show us the horizontal and vertical position of the ball in this case, and it's going to say our distance clear, which we specified as 5, is going to be a vertical dashed red line, and we're going to see if the ball exceeds that red line, if it clears that red line. The other thing I'm going to do is I'm going to go ahead and display a few things so it's a little bit easier to follow. So what we're really interested in knowing is the distance cleared greater than 5. So I want to print out to the user the distance cleared. So we'll use num to string, and we're going to call in position x, the last value in that position x variable. And this loop is running, right? And it's appending to position x on every loop. And as soon as this loop stops ending, so as soon as that ball hits 0 in the vertical direction, we want to know how far it went in the horizontal direction. And so this loop stops, the code stops when when vertical position is greater or less than or equal to 0, and we want to know what was the position then. So we call position x end, the last value in our position array. We also probably want to know what the time was. You remember when we calculated the time, it was like 0.65 or something. So time passed, and we'll again call num to string because these are numbers and we need to convert them to strings before we display them. Time end. And then let's see, another common thing that people like to see is the peak height. Like, what is the peak height when you kick a ball at this velocity at this launch angle? So we'll also call peak height. How's that? Okay, again, num to string. And what we'll do here is we'll call max position y. Okay, let's see. Let's see if this runs. Okay, there we go. So again, our horizontal displacement when we calculated it by hand was 2.49 and our time was 0.65 seconds. Our distance cleared here, 2.49, that's good. Time passed, 0.66 seconds, so that's a little interesting. So time passed is slightly different, it's off by 0.01 seconds. And peak height is just over half a meter, 0.5. Okay, so this code looks to be running pretty well. The last thing I want to do is, and we can change stuff like this, so we can say, let's go ahead and give it a launch angle of 20 degrees and see what that does. The velocity stays the same, we're just changing the angle. Now our peak distance is 1.5, right? Okay, and we can go higher. Let's give it 60 degrees. Our peak distance is 2.2. All right, so we can go ahead and change different things in here. We could go back to 40, and we could change the velocity at which we kick the ball to 10, so we could double it. See if we clear 5 doing this. Oh yeah, we got no problem clearing 5 when we do that. Right? So you can change things like that. The other thing that you could do is you can change the time step, right? So let's change it to 0.1 and see what happens. So now instead of going through and basically sampling velocity position at 0.01 second changes in time. Let's do it at 0.1 seconds in time. Okay, now, let's go back. I forgot that I had changed this. 10, 40. We're still looking at 5. Let's go back to our initial values of 5, the question that we started with, 5 and 40, 0.1. And let's just compare that to what we got when we did it at 0.01. So now it's 2.29 compared to, what did we have before? 2.49. So you'll notice that the distance is off, and it's because we're sampling at different rates. And the last time that it took a value was different. So it's always good to sample it. It was not always good to sample at higher rates, but in this case, 0.01 worked out really well for us. So that's just something to keep in mind as you're going through these problems. And then especially as you start to do research, this is something to really think about when you're looking at sampling frequencies of different pieces of equipment. Okay, I hope you liked that video. In the next video, what I'm going to do is optimize launch angle for a given velocity, which is going to be very, very similar to what I did in video 2, where I minimized velocity to clear a given distance. So look forward to that. If you liked this video, give it a like, share it. Please subscribe to my channel. I'm going to keep pumping stuff like this out. And you can also find me on Twitter, LinkedIn, GitHub. Of course, I'm here on YouTube. And I think that's it. All right. Until next time, keep coding.